welcome everyone. Today's speaker is Augusto Teixeira from IMPA and IST, and he's going to talk about percolation on randomly stretched lattices. Augusto, thanks for accepting our invitation, and the floor is yours.
Thank you. Can you all hear me? Great. So it's great to see IMPA's room crowded again. Thanks a lot for the invitation. So, and I gave this seminar last year, and I was in Rio, but at the time it was lockdown. Then I'm in Lisbon, but the room here is packed, is booked. I'm planning to give this talk next time in Buenos Aires and then Arizona. Let's do the whole tour. So today we're going to talk about joint work with Marcelo, Marcos, and Remy. So it's a second of a series of works we're trying to do on percolation. It's a modification of the standard percolation, but we're going to start with the standard one, trying to give some motivation, and then we're going to spend a good deal of time in some ideas of the proofs. Thanks, Fabio. And I hope it will not be very heavy. I tried to keep the proof just in the overview style. And I also hope to finish earlier so that it's not very tiring. And then we'll talk a bit about the takeaways from the model and the proofs. So percolation in general, in its simplest form, was introduced by Broadbent and Hemsley in the 50s. It has been studied a lot, both in physics and in math. It's actually a very simple model. In physics, it could be said that it's kind of understood. Physicists understand the model in quite a bit of depth now. And all of these statements from the physics community are still most of them are very open from the rigorous perspective. So we're going to see a little bit more what I mean by that. So start with the Z2 graph. So just take the points in Z2 and join them by edges when they are nearest neighbors. Then we fix a parameter P that's going to regulate, govern the density of connections. And then for every edge, independently of one another, we toss a coin, and with probability P, we keep the edge, and with probability 1 minus P, we close it. So this gives rise to a random graph. You can see there a little sample in a square. And we're going to be interested in the connectivity properties of this graph. More precisely, let's stick to this quantity here. We're going to study the event that the origin is connected to infinity, meaning you can find an infinite self-avoiding path that only crosses open edges and starts from the origin. Please?
May I ask you a question? It's a very silly question. So your pictures are actually random or not?
Yeah.
And what is the P then?
I don't remember it, but it's super critical.
Okay.
So this is not a serious simulation. I call simulation by ticks. So ticks is this program that you can write inside the LaTeX to do drawings. And it has loops, it has randomness. So it's probably not a very serious simulation. The random number generator is not trustworthy. But I made sure to choose the parameters in a way that I could find the path. And there will be other simulations for the other models that did the same way.
Yes, thank you.
And so please interrupt me anytime, because as I said, I prepared the talk to be shorter. So theta is going to be defined as the probability of the event above. The probability that you find is infinite path, and it's a proxy for how well connected our lattice is. There is a beautiful argument from the physics that proves that for p smaller than 1/3, so p from 0 to 1/3, the probability to find such an infinite path is 0. So if theta was an analytic function, it would be 0 everywhere, right? Because it's 0 in a whole interval. But surprisingly, if p is larger than 2/3, then theta is positive. So theta has to undergo some sort of phase transition, which is the name physicists give to the phenomenon that a function like this defined naturally, which is always analytical in finite networks. Like if we were considering urging connected to the boundary of the box, theta would be analytical. It ceases to be analytical when you take the limit to infinity. So this is a plot of what we expect theta to look like, 0 up to some critical value. And then, although it's continuous at that value, its derivative is infinity, and then the rest is analytical. Actually, for dimension 2, this is all proved. So we know that PC is this point where the function ceases to be infinity, ceases to be 0, is the only point where theta is not analytic. Harris and Kasten proved that for the specific lattice we talked about, PC is 1/2 exactly. And theta is continuous everywhere, analytic except at that point. There are still many, many questions, especially in dimensions 3 up to 10. We don't know if theta is continuous. It's not expected that the question is the same difficulty for all these dimensions. Dimensions 3, 4, and 5 are especially hard. Then 6 to 10 are expected to be somewhat easier. For reasons that escape the talk, the subject of the talk. And the way in which theta approaches 0 as p approaches PC is also understood in high dimensions, larger or equal to 11, and in dimension 2 for one specific lattice, which is the honeycomb lattice, not the square one. For the square one, it's still a very big open problem. But we're not going to talk about this model. We're going to talk about the modification of it, but it's good to keep that in mind. So the modification we're going to introduce is, yeah, please.
When you say honeycomb lattice, you mean like the sides are hexagons, right? So side percolation. Yeah, okay.
So it's supposed to be the triangular lattice actually, where you're doing sides in the triangular lattice. But if you look at the Voronoi thing, it would be hexagons, like the faces. So this model has some very beautiful symmetry that like the square lattice, it doesn't have, and it's what allows people to understand what happens at that model, but not in others. Okay, so concerning the model we're going to talk about, we're going to introduce some defects along the lattice, and we're going to ask the same questions, but of course we're just going to answer the first one about the existence of a phase transition. So the defects that we introduce go like this. There are two ways to introduce this model. So the first one is, forget everything that's written, look only at the picture. The first one is you take these lines of vertical edges and these rows of horizontal edges, and each of them you toss a coin, and with some probability you delete the whole thing. And you're left with this lattice that's kind of stretched. A completely equivalent way to define this is to take psi i's, psi 1, psi 2, and so on, to be geometric random variables. This geometric is the successes that you had in the coin tosses I mentioned before. And you space your lattice with these geometric random variables. So you see that, for example, psi 1 is what is 5 or 4, So it means that we're going to put a vertical line of edges here, then we're going to skip 3 and we're going to put 1 only in the 4th. So here you can see the coin results, the coin tosses, and here you can see the inter-arrivals, which are geometrically distributed. So this is just a preparation, right? We're just preparing a stretched lattice, and we do this in the 2 axes at the same time. Now we are left with something that looks very much like Z2, but it has these thick columns that are very hard to cross, because now we are going to do independent percolation here. So if you want to go from this point to this point directly, you have to open all these edges here. So that's fine. I mean, we are going to try to do very large values of rho, which means this is usually only 1. So we're gonna have to wait only 1 attempt to have a success. So typically it's gonna look like the square lattice, but sometimes you're gonna have these big holes here that are hard to cross. So is the model clear for everyone? So here's a simulation of the model. As I told Milton, we did the simulation in a way that there is actually a crossing from left to right and a crossing from top to bottom. And unlike in the case of percolation, that if you want to find this cross, you just start looking and you find it. Here, you actually, it is a better strategy to first look at this. You see that there is a column here that has been very damaged vertically. First, find the crossing there, and then you extend it to the left and to the right. If you start looking greedily from left to right, you're gonna probably find yourself in some dead ends, and then you have to backtrack and so on. So first, you work your way through the hard passages, and then you complete. That's also a bit the spirit of the proofs that you're going to see. So first, take care of the hard parts. The rest is kind of easy. So this is the first time the model appeared in the literature. It was in a paper by Jonasson, Mossel and Peres. They introduced other models with what they call axis aligned defects, so defects that are aligned with the axis. And they proved that those models have a phase transition, but this one they didn't manage to prove there, so they conjectured that if you take the row very small, so you have very few defects, and P very close to 1, so you keep most of your edges, then you have percolation. It's worth noticing that the absence of percolation is trivial, because the stretched lattice is weaker than the square lattice. So if you're below 1/3, you didn't percolate, so you already don't percolate in this one. Actually, it's more than 1/2. But the existence of percolation is difficult to prove due to this stretching and this harm due to the network. Also, the original argument by Piers fails because of the dependence introduced by this. Yes?
So here you're requiring both rho small and P large, but I don't know, it seems that there is some kind of invariance in the system. So if you have rho arbitrary and if you take P large, then this should be sufficient. Exactly. I mean, the conjecture should be equivalent, right?
Yeah, so the fact that you can go from this statement to a stronger statement that it says, for every row there exists a P large enough, that's the easy part. It takes one block argument. So I just didn't include it here because I want to focus on the hard part. So this conjecture was first proved by Bramson, Durrett, and Schulman, actually before it was conjectured. So in the case that you only have vertical defects. So the conjecture was for vertical and horizontal ones, but before that thing, Bramson, Dirt, and Schaumann studied the contact process with some defects. And I have not entered into the details, but as a corollary, they prove the above conjecture when you only have vertical defects. We have an extension of this BDS theorem where we only keep vertical defects, but we allow the interspace between them, between the columns, to be not geometrically distributed, but have heavy tails. So you can have, as long as psi has moment of order 1 plus epsilon, you also percolate. But here again, only vertical defects. The case where you actually have vertical and horizontal defects was proved much later by Hoffman. So he proved exactly the conjecture that exists a small enough rho and large enough p such that you percolate. We are going to review that result. The original result uses what we call dynamic renormalization. I'm going to explain what this means soon. And we're going to present here a proof that uses static renormalization. It's also inspired by Hoffman's, but it's, in our view, easier to follow. Questions? Okay, so, yeah.
Are there any, I probably asked this question in the past, but are there any conjectures for in 2 dimension when things are, the tails are just a bit heavier than exponential?
Oh, very good question. So we have a theorem now that says that Hoffman's result is very sharp in the following sense. So I'm gonna hand wave a little bit because I didn't have the statement written down, but basically says, if in one of the axes you have something heavier than any exponential, so you don't have any exponential moment in one of the axes, and in the other axis you don't have compact support, then there is no percolation. So Hoffman is as sharp as it gets. You need geometric in both. If one of them is slightly heavier than geometric, the other one either has compact support, and then it's basically periodic, right? Or you don't have percolation.
If you have Gaussian tail on one side, then geometric is still required on the other side.
Exactly.
Okay.
So another question. So the phase transition diagram you expect it to be the same as in the usual percolation?
So it's very different from usual percolation. For example, in usual percolation, if you have percolation, right, if you are supercritical, you cross boxes with a probability that is exponentially close to 1 with respect to the size of the boxes. So if you have a box and you're supercritical, you're most very likely to cross it. Here, you always have a polynomially large probability that you don't cross. So it's like you always have this, what physicists call the scale-free stuff. So I always have heavy tails, even if you take the parameters very close to their extremes. Okay, so let's rephrase the model. It's what I'm going to say here is perfectly equivalent to what I said before. So we are going to assume those geometrics can have value 0. So now we have to sum 1 on them. Otherwise, it would be probability 1, right? If they were 0. So we are going to treat exactly the square lattice, not the stretched version. But we are going to require that to cross an edge, you don't have to pay P, but you have to pay P to the psi I plus 1, where psi I is the corresponding variable here underneath. So it's exactly equivalent, but now we are dealing with the square lattice, which is more convenient to identify edges, to like make indexing. Now our sums are no longer random, right? So the proof will go through two steps. First, we deal with the environment, just the size. And we're going to show that with high probability, the size are good. And after we prove that the environment is typically good, we're going to show that no matter what environment to take, even if it's deterministically picked by your enemy, if they pick a good environment, you percolate with positive probability. So you see that there are two steps, one for the environment, the other for the percolation, just like our model has two sources of randomness. And between these two steps, there is a contract. And this contract is what it means for an environment to be good. And the first part shows typical things are good. The second part shows any good thing is good enough. And as I said, we use a renormalization technique. My favorite type of renormalization is this one that we call static. So just pick a sequence of scales. Here we pick a geometrically growing sequence of scales. LK is 500 to the K. And we pave the lattice with intervals of this length. So you can see that here's a picture of this paving. It's not very advanced, but you can see that an interval in scale K plus 1, like here, the blue one, is formed by 500, here it's only 4 to simplify the picture, but 500 intervals in the previous scale K. So the scales paves at D with disjoint intervals. Not only that, they are nested. One is composed by a disjoint union with the previous one. Okay, that's as nice as it gets for multi-scale renormalization. And this slide is the one that has the whole idea of the proof, but I don't expect everyone to follow. So this is going to be a heuristic, and we're going to go through all the bullet points in this slide with more detail later, but this is the summary. So I've told you that there are two steps, the environment and the percolation one. In the environment step, we are going to give scores to intervals. So every interval is going to be labeled depending on how hard they are to cross. And you see that, let's say we give score H1 to this interval here and score H2 to this interval here. We have to decide, based on this, which score we are going to give to the big interval that contains the two. And recalling that the probabilities of what's occurring here and here is independent, because our geometrics were independent, we expect the probability to be multiplicative, right? The probability of something happening here and something happening here is going to be multiplicative. So the labels, if you put them in the exponent, they become additive. So somehow we expect, if we give label H1 to this interval and H2 to this interval, the big intervals perhaps should be labeled with H1 plus H2, where Q to the H is the probability of finding that kind of defect. So this is the heuristics behind our labeling. That should be additive and the probability should be in the exponent. Now in the percolation, a different type of thing plays out. We are going to keep track not of labels, but of armies. So what's an army? We're going to take a column like this, where underneath we have some interval that we want to cross. So this column is just the interval times Z. It's infinite. So we put right before the column an army of points with a certain size, and we see how many crossings we have and how many soldiers we end up to the right. So if we start with something, we end up with something, and we expect to have losses that are again multiplicative. So if we have 2 columns in a row, we're going to lose some soldiers, then we lose more soldiers. So this is why we put the number of soldiers as something in the exponent. And we're going to be subtracting the exponent as we cross a defect. So you see we had here 2 to something plus h, which was the type of defect we are crossing, and we end up with 2 to the k. We lost h in the exponent there. It's like saying that more or less every soldier dies with probability 2 to the, survives with probability 2 to the minus h. So this is the 2 ideas that we're going to detail more along the talk. But this is what took us the longest to figure out. This very simple algebra that you should be summing in the exponent in the first part, subtracting the exponent in the second part, and that's it. Questions? Okay, so let's do the environment thing I told. So I said that the previous slide was very informal and heuristic. Let's make it more rigorous. I said that we want to grade defects. That means for every interval I at scale k and position j, we're going to associate a defect hkj. And this defect is an integer, could be 0, 1, 2, and so on. If the defect we associate is 0, this interval is called good. Otherwise, it's called bad. And how bad depends on h. Could be 1 bad, 2 bad, 3 bad, and so on. Of course, the highest the badness, the harder it is to cross. At scale 0, everything in multi-scale renormalization is done by induction, right? We define everything in scale 0 and then go from scale k to k plus 1. Then we prove something in scale 0 and we prove that it can go from scale k to k plus 1. So at scale 0, we're going to define. Of course, we already defined our scales to be 1. So our intervals are just single sites. The site at position j is just the site j. No surprise there. And this site is associated to a certain psi, right? This is going to be the intensity of our defect. So at scale 0, every point has a certain psi, and that's how bad it is. We only call a site good if it's 0 psi. So that means to cross that edge, you need p, not p to anything, any power. And how do we go from one scale to the next? It's what I showed in the last slide. So if all the sub-intervals, the 500 of them, are good, we say that the next scale is also good. No surprise there. If they have defects, let's say J0 up to JL, like this, all these guys are bad. Like this is these are the scores they get. Then the big scale is going to sum the scores of its children. Except that we need one exception. If there is only a single bad subinterval, then we don't just copy it, which would be summing, right? Imagine that you have 0, 0, 0, 5, 0, 0, 0. Then you just don't say the big interval has intensity 5, you subtract 1. You are introducing some sort of healing. And this is necessary, if you think, because the way we are defining, if we didn't add this exception here, then there would be no good intervals at high scales, right? Because if you take a very large scale, there will be some side different from 0 inside. And if you just keep summing everything, the big scale would be at least that dust. But by introducing this exceptional case here, we are saying, okay, if you find something bad, but it's surrounded with good things, it's slightly better in the next scale. Is Hubert reaching for the microphone? No.
Yeah. So just to make sure you're doing the grading like in a really independent fashion for the horizontal variables and the vertical variables.
Yeah.
Okay.
Exactly.
And why don't you subtract just 1 to everything? So on the second line too.
Yeah, after you you find one thing that works, it starts to become very easy to find several things that work as well. So we could do this. We could sum, in the second case, we could sum 20 here. That would be fine as well. We could subtract 20. But, oh, sorry, one of the cases I'm lying. No, you cannot subtract here. We have to subtract here. We could subtract 10 instead of 1. We cannot subtract here. We have to add here. We could add 1, add 20, or not add anything. So the reason is going to become clear by the end of the proof, but the idea is the following. Subtracting anywhere here makes your life easier now. But when you're trying to percolate, everything that you subtracted here becomes a problem for you. Summing something here makes your life here hard, but it makes your life easier when you're percolating. So remember, there is a contract between the environment and the percolation. And this formula is the contract. Subtracting here makes it easy for one side and harder for the other, and vice versa. So here's the lemma that we actually prove. If you choose your constant of defect small enough, the probability to find the defect of label K decays very fast with defect H, decays very fast, both with the scale and with H. You may think that this is an exponential decay, but because everything is the exponent here, but you should think of this more as a polynomial decay, because the box at scale K that we're talking about, it has length 500 to the K. So this is like an exponent minus 10 and an exponent minus 20. It's a polynomial decay. That's related to what I said to Newton, that the decays are not exponential. Even in the supercritical phase, they're polynomial. Let's prove this with a fake proof. So at scale 0, you just observe that having label H is the same as having the psi be equal to H, which is rho to the psi with a geometric random variable. And that's smaller than this if you choose rho small enough. So for the scale 0, it's just choosing rho small enough. Now the induction. Suppose that this is true for a certain scale. Let's prove it for the next scale. What's the probability that you have a box with label H? Okay, you have to sum over all your sub-boxes. The labels that sum up to H. And now you have to have all these labels. This is a product because things are independent. So you have a product over the sub-boxes of the price you know you have to pay by induction, by the induction hypothesis, to have that label in the sub-box. So it's 500 to the minus 10K minus 20 HI. So the label you gave to the box I. So this product becomes a sum there, like I said in the heuristic slide, and the sum there of the H give you H, and you're done, except that we completely skipped here the entropy term. Right? There are so many ways to find boxes that sum up to H. So here there's an entropic term that we've completely swallowed. If there wasn't, then this would be a proof. And the way to do this, to make this work, is to use the recovery. So that -1 is crucial for this to work. After you have that -1, this proof, with a slight modification works. You just have to know how to use the recovery. Any question? Okay, now let's turn to the environment. So as I said, in the environment, we're going to take columns with some interval here, with some badness. We're going to set up an army to the left and see how much of it survives. So we're not going to consider any army here. In renormalization, usually you define these things by induction again. So we're going to consider, so why can't we consider any arbitrary army? Because if it was too packed, like an interval, then its size wouldn't be very representative of its power. Like if you have a packed army, it's very easy to surround it and kill it. It's the military analogy here is perfect. So if your army is packed here, it's very easy to kill it. So we're gonna define the allowed sets as to be of the following form. They have to be a kind of a fractal. First of all, they have to be in a good interval, because remember, we are trying to cross something horizontal here, but there is stuff happening in the vertical axis as well. And if you put your army inside a bad horizontal block, stripe, it's kind of doomed already. It's not going to be efficient. So your SK has to be in a good interval. And moreover, it has to be a union of 16 disjoint k-1 fractals. So it's basically an induction hypothesis. What's a zero fractal is a point that's a good point. What's a one fractal? It's 16 good points. What's a two fractal? It's a union of 16 one fractals, disjoint. So now we know what kind of army we are dealing with. And the most important definition in the talk, in the second part of the talk, is that of VK. It's the probability that for some type of thing you want to cross, some defect, and some army that should be enough to cross that defect because it has size 2 to the 4k plus the size of the defect, you don't end up with a big remainder. So RK is how much you're left here in the right. So as I said, we're going to subtract things in the exponent. So if you start with 2 to the 4k plus h, you should end with 2 to the 4k. And the probability that this doesn't happen for some h, for some s, is the probability of the bad event that we want to bound from above. Observe that we really don't restrict anything in the vertical space here. The S could be very spread out, doesn't matter. And observe that the loss we incur in our the number of soldiers is multiplicative. It's here happening in the exponent. So let's see how this behaves. Yes?
So somehow, like this 2 to the 4k corresponds to the spread outness you require. So when you augment h, k, I don't know, you don't require some extra spread outness. The way you reinforce your army to cross worse stuff, I don't know if I understand things well, does not require it to be more spread out. Or
exactly. So there are two parameters here, right? K is the size of the basis. So this interval you're trying to cross is in scale K. And how bad it is, which is H. The S should be kind of many K fractals. So the sparseness is only determined by K, as you said. But then you could just join a bunch of them in a row, and that would be fine. How many of them? 2 to the H. Okay, so with that definition, the proof is going to be just like the environment case. It's going to be just induction. So that's the statement. If you choose P very close to 1, then the probability that good things don't happen, like bad things happen, is very small. Again, this is not an exponential decay, this is a polynomial decay. And first observation, if we have this, we are done. Because we can use this to take a small army and keep moving it around and dominating the universe and build an infinite cluster. This is typical, like in Bernoulli percolation, you also do like this. You start to construct a stairway. As soon as you can cross boxes very well, you build a staircase with growing tiles and you survive. Hello, can you hear me?
Yes.
Oh, just my video dropped, but okay. So as soon as you have this lemma, you're done. Now, the proof is again induction over K. How do we prove the zero case? It's very easy. So in the zero case, let's go back one slide. You have just a single column with thickness 1, and you have an army, and just try to cross, like crossing that edge. It's a binomial. So if you start with K guys, K is not a good name because it's the scales, K is 0. If you start with J guys, you end up with a binomial J P to the psi, P to the H. So we know everything about binomials, just a concentration to show that this is true at scale 0, just a concentration of binomials. Now we have to go to the step K to K plus 1. So suppose that we know how to cross columns of width K. Can we cross slightly larger columns? So just as in the case of the environment that we consider two cases, either there is a single defect inside the box, then that's the healing, or there are multiple defects. Here again, we have to do this distinction. So we're gonna consider multiple defects and single defects. So this is the case of multiple defects. So you see we're crossing something of larger scale, and inside there are two defects of scale K. So you see the small defects are H1 and H2, and the big one is H. We start with an army that is supposed to be enough to cross the big thing. So it has size 2 to the 4H plus H. Sorry, 2 to the 4K plus H. And you see H is the sum, so you can write it as such. Crossing the good part doesn't reduce our army. It's a lemma that I didn't show. But if you start here with some number, you end up right before the first barrier with the same number. Now, as you cross the first barrier, you lose that H1 here, the exponent. That's the induction. Then you don't lose anything in the interval here again, because it's good. You arrive right next to your second barrier with this, and H2 is enough to cross the second barrier, and you're left with 4K, and you just keep 4K up to the end, and you're done. So a lot of hand waving, but you see that the fact that the thing multiplies is what saves us here. Cross several columns, the exponent starts to drop. And what happens with a single column? The proof should be identical, but it's not. Let's look why it isn't the case. So you have something at scale, at the big scale, and here you have something at the smaller scale. Observe that the relation here is different because there was healing. So remember that we had to introduce healing in the beginning of the article to make the environment work. Now we're gonna have to work harder because you see, we are crossing something of a defect of label H. So this is how much we have, 2 to the 4K plus H. And when we arrive to the small defect, it's of label H plus 1. So it's gonna eat our H here and still eat a bit more. So we are left with less than what we needed. So what I'm saying is that, okay, you're left with something that's not enough here, but you still have some good regions. And in the good regions, you actually can increase a little bit your arm. But then you can say, okay, but what if the defect is right next to it's the end here? Okay, so I recover before. Before I reach the defect, I add 1 here. And then when I cross the defect, I'm fine. So when you have a single defect, you always have a lot of good parts, either to the left or to the right. And in that part, I'm going to use the fact that I'm walking in good territory to increase my army and make everything work. So of course, I'm skipping a lot of details, but this idea of how the proof is structured is there. This is the idea, not cheating in the main outline of the proof. And you can think like this to solve other problems. So that's why I wanted to illustrate this. For example, I could have taken the same idea and showed how to prove that oriented percolation here also survives, or that the contact process with this defect also survives. So the overall sketch is very robust. So I said I would end with some takeaways. So first is my favorite reason to like renormalization. Although renormalization has this bad record of being technical and you have to do induction and sometimes it's not intuitive, I find it very compelling because of the storytelling behind. You see that we were talking about difficulty to cross something, and then the army arrives and the soldiers die. And whenever I use renormalization, I can see the underlying storytelling. So that's why I like the technique so much. There was this contract between the environment and the percolation. And I would like to advertise that renormalization in this when you have two sources of randomness is very underdeveloped. I think we should try to take more models that have this quenched and annealed sort of construction and do randomization in them to develop the technique, also to prove nice stuff. And whenever you try to do this, you need a contract between the first source of randomness and the second. And the contract here is done by this, I mean, I'm calling it an algebraic interplay, although this is a very ambitious name. It's just that you sum in the first part and you subtract in the other part. So that's the algebraic interplay. There is this slight exception that you don't sum if you have only one, then you subtract one. And we can list, and we list in our upcoming article, several different models that we believe could be treated with this type of technique. So the Cox process is something that we don't know how to do yet. We believe that there is some hope to use these techniques to prove stuff about this model. But it's a very simple model to state, and I have no idea how to prove that it has a phase transition. And it's natural, the Cox process is natural because it's something used to model satellite networks. Extending this problem to higher dimensions sometimes leads to trivial results, right? Just like when you prove percolation in the plane, you automatically have percolation in the three-dimensional space because the plane is contained there. But depending on the way you generalize, it becomes hard and you don't know what to do. You can also try to look at other models at independence, and, you know, the sky is the limit. So I'd like to thank you very much and put some pictures that show the relation between Lisbon and Rio, which is not restricted only to streetcars. Thank you so much.
Thank you very much, Augusto. You can clap. So you manage your time perfectly. So we have time for questions or comments? Let's see. So there is something that I didn't understand regarding the conjecture. So I would expect for the rho and the p to be dimension dependent. So it was proof for dimension 2, and then it's still a conjecture for higher dimension.
Yeah, for dimension 2, there is some, for every row there is a p.
Okay.
So this is kind of a critical curve. We know very little about this curve. I mean, we know nothing about this curve, but there should be a curve. And when you grow the dimension,
Mm-hmm.
the existence, there are several ways to grow the dimension. One of them is the more intuitive one. You just add your spacing everywhere. The 3 dimensions, say you add spacing here, here, and here. Now it's very easy to prove that there is a phase transition because if you survive in the plane, you survive in 3D. So, but it's not so trivial to show that the question of Newton is still true. Maybe depending on the way you generalize to 3 dimensions, you could have an exponential decay like when I was answering Newton. Also, depending on the way you generalize to 3 dimensions, we don't even know if there is a phase transition.
Right, right. Because also,
for example,
no, also the critical value for the phase transition should be dimension dependent.
Yeah, this whole curve should change completely depending on the dimension. For example, this model is very related to the contact process. I didn't talk anything about, didn't mention this relationship, but the contact process has naturally this axis aligned defects, because if you have one individual that is more susceptible to disease, it's gonna be a whole line in your space-time that behaves differently. So when you go to the contact process in 2D, then you have 2 physical dimensions and time. Then you have open questions, still a lot of open questions, because showing that this contact process survives is easy, because if it survives in 1D, it survives in 2D, but showing that it dies becomes the challenge. We don't know how to do that yet.
Mm-hmm. Mm-hmm.
So imagine you have a population, 2D population with some very susceptible individuals, but this big susceptibility is just a geometric. Like every individual has a susceptibility to a geometric random variable. Is there any hope for the infection to extinguish? Because it could be that some person can hold the infection for long enough that it managed to travel to some other hub elsewhere and it never dies.
I see. Interesting.
Yes.
So you said there is nothing known about how the critical P belongs as a function of rho, but I don't know if you take if instead of taking geometrics you take exponentials, then the critical P would just be okay. I mean the exponent changing the function of the exponential is just changing P by some power, right? And when rho is close to 1, I don't know, geometrics and exponentials, it should be kind of the same. So at least, okay, I don't know, it's apart from these integer effects, maybe you should have a relation between the critical P for different values of rho.
So you're saying if we take
just by domination
process, you take the Poisson process in each axis and you put the lines, then you can change the P by some change in the rho and get the explicit, like some sort of, maybe you can even get the explicit curve.
I think, if you replace geometric by exponential, then the curve should be explicit, and then maybe if you in the exponential, you probably can compare the curves for 2 rows for this reason.
Yeah,
compare the values of PC for 2 rows.
See. if there are more questions or comments. If I don't think it's the case. Okay, so thank you so much, Augusto.
Thanks a lot for the invitation.
And we update next Wednesday, same time, same place. Bye-bye.
I see you.
Bye. Ciao, Pablo. Bye-bye.
Bye-bye.